Hello, everyone. Thank you for joining us tonight, and we want to welcome you to the first public lecture of 2024. This is the United States Geological Survey Virtual Public Lecture Series, and I will be your host and moderator tonight. My name is Christy Ryan. Before we get started, I do want to just go over a few things about this Teams Live platform, just in case it's your first time using it. If it is your first time, welcome. If you've been here before and know these things, thank you for coming back. One great feature of this platform is the question and answer panel. You can go ahead and find that by looking in the upper right-hand corner of your screen for the Q&A icon. And this is where you're going to go to submit any questions you have for our speakers tonight. And I do encourage you to submit questions all throughout the talk. You don't have to wait until the very end. But at the end is when I'll go through all the questions and ask them of our speakers. And of course, we'll do our best to get to everything. Depending on how many we get, we may not have a chance to do them all, but we're going to certainly do our best. Another great feature of this Teams platform we want to point out is the closed captioning option. So if you're on a desktop computer, you can just look at the lower right-hand corner for the CC icon, and you can turn on closed captions that way, or you can use the stream text link that I just provided in the Q&A box there. One quick little thing before we get going is I did want to take this time to give you a heads up about our lecture for next month. On February 29th, we will have the pleasure of welcoming Dr. Sarah McBride. She's a USGS research social scientist who will be giving a talk titled Using Communication Science to Communicate USGS Science. So please mark your calendars and join us then. At the end of this lecture, I will give information on how to join our mailing list, and that way you'll receive emails of our upcoming lectures, so you'll always know what new and exciting topics we have for you. So now that we've gotten all that business out of the way, let's go ahead and get started for tonight. Tonight we have the pleasure of welcoming two speakers, Kathleen Springer and Jeff Pagati. Kathleen is a research geologist with the U.S. Geological Survey in Denver, Colorado. She specializes in deciphering complex stratigraphic sequences and reconstructing paleo-environmental conditions. She also studies how springs and other hydraulic systems responded to climate change in the recent geologic past. Jeff is also a research geologist with the USGS in Denver. His research is focused on understanding the response of hydrologic systems in arid environments to past episodes of abrupt climate change. He's also an expert in radiocarbon dating. So at this point, you've heard enough from me. Let's go ahead and give a warm virtual welcome to our speakers, Kathleen and Jeff. I believe Kathleen's going to kick us off. So Kathleen, the floor is all yours.
Hey. Here we go. Just want to make sure you all can see it well. Does it look good, Christy? Sounds good.
It is pulling up. There we go. You're all set.
All right. Well, hi, everyone. We are really super excited to share the work that we have been doing for the last few years in White Sands National Park in beautiful New Mexico with their really amazing park staff there and in collaboration with an international team of researchers. So in a nutshell, humans and extinct Pleistocene animals are being discovered together there. Remarkably, not in the form of their bones, as you would think, but in the form of their footprints. And the National Park Service invited Jeff and me to be part of this team to help the park understand the full context of these prints and critically to really get a handle on how old they are, because the potential that they are of great antiquity has really important implications about the peopling of the Americas. So, we set to work, and in 2021, we published our first set of findings in the journal Science in a manuscript entitled Evidence of Humans in North America During the Last Glacial Maximum. And spoiler alert, that's 26 to 19,000 years ago. So we're going to get to that. So we're really thrilled to present this work and to show you how we went about getting our results. Really the questions that we asked and the methodologies that we used, and how we addressed the inevitable controversy that arose from the original work. And we're going to share our latest results that were published just recently in October, again in the journal Science. So Jeff is going to get us started, and he's going to set the stage for what was known about North American archaeology prior to these discoveries at White Sands.
So our story starts with George McJunkin, who was a cowboy and an amateur historian living in eastern New Mexico. And importantly for us, he was also an amateur archaeologist. So after a flood near the town of Folsom, New Mexico in 1908, he was out checking fences when he discovered several large bones that were sticking out of the sediments that were exposed when the floodwaters carved a deep arroyo. And among these bones was a distinct type of stone tool, which we now call a Folsom point. So he recognized the significance of the find, and he left the site undisturbed except for recovering a few sample points. And for several years, he tried to interest archaeologists with little success. In 1919, the Denver Museum of Natural History sent out a paleontologist to examine the site, but it wasn't until 1926, nearly 2 decades after the original discovery, that a thorough excavation was finally conducted. Now, it turns out the bones were from an extinct type of bison, and among these bones were beautifully preserved projectile points, or what we used to call arrowheads. And here's a beautiful close-up of the bones in an absolutely spectacular Folsom point. Shortly after the Folsom excavations, another important site called Blackwater Draw was discovered in 1929 near Clovis, New Mexico. And at Blackwater Draw, archaeologists found a number of Folsom points scattered among the remains of late Pleistocene megafauna, including mammoth and camel, horse and bison, saber-toothed cat, giant ground sloths, and even dire wolves. Deeper in the sediments, and therefore older, they also found several large fluted points, which are now known as Clovis points. And at least 9 of these Clovis points, including the big wide point second from the right here, were actually found within mammoth skeletons. Over the following decades, dozens and then hundreds of Clovis sites were found across North America. All total, archaeologists have discovered more than 10,000 Clovis points scattered across about 1,500 locations covering most of North America. Radiocarbon dating that began in the 1960s showed that these Clovis points date to about 13,000 years ago. So for decades, archaeologists believed that Clovis people were the first to reach the Americas, and this idea of Clovis first was born. Now, interestingly, people at this time didn't just stop in North America. Several archaeological sites in southern South America include similar points that date to the same time period, which shows that Clovis, or at least related cultures, expanded to all of the Americas in very little time. So what were they like? What were the Clovis people like? Where did they come from? What were the conditions like when they arrived? And what types of animals did they encounter when they got here? What little we know about the Clovis people comes from the tools and other evidence that they left behind, which suggests that they basically consisted of small bands of nomadic hunters who preyed upon Ice Age animals to survive. DNA evidence shows that Clovis people likely came from Asia, through Siberia, across the Bering Strait, and then down through Alaska. But during the Last Glacial Maximum, large ice sheets extended across Canada and the northern United States, and these ice sheets were massive. In the Seattle area, for example, the ice was about 3,000 feet thick, so this would have blocked passage from Asia. But by about 13,000 years ago, the ice sheets had shrunk significantly, which allowed people to come down south along the coast, which is called the coastal route, or inland through what is called the ice-free corridor into what is now the continental United States. In the southwestern US, we like to say that this time period was basically the ice ages without the ice. There were large lakes everywhere, springs and wetlands were present in many of the basins, and what people and the megafauna needed most to survive, namely food and water, were plentiful. The animals that the Clovis people encountered were nothing like what exists in North America today. Mammoths and mastodons, camels and giant ground sloths, extinct horses and bison, and carnivores like the American lion, saber-toothed cats, and dire wolves, kind of all of the classic Ice Age animals were present. Now, over the years, there have been a number of challenges to this idea of Clovis first, but many of these, what are called pre-Clovis sites, have not been accepted by the archaeological community, either because the artifacts turned out not to be artifacts, the stratigraphy was incorrect or misinterpreted, or the dating turned out to be wrong. But nevertheless, there were a few pre-Clovis that have stood the test of time, and collectively, they pushed back the peopling of the Americas to 15 or maybe even 16,000 years ago. This was essentially the state of our understanding of the earliest phases of North American archaeology when we began our work in January of 2020.
So that brings us back to White Sands National Park in southern New Mexico, where they have been finding evidence in the form of footprints of people and trackways of all kinds of extinct Pleistocene megafauna together for over 15 years. And here is artist Karen Carr's rendition of such a scene. So what is the setting of these extraordinary finds? White Sands National Park is located within the Tularosa Basin in southern New Mexico, and Pleistocene Lake Otero occupied this basin, as did many other pluvial lakes and similar basins throughout the American Southwest. White Sands is the largest gypsum sand dune field in the entire world, and it's made up of sand from this Pleistocene age Lake Otero. And they've been deflated by this never-ending wind that scours the basin there. But there's very flat-lying lake deposits that transition to lake margin sediments that are still exposed on the edges of this basin. And this is the setting where we find the tracks and where we did our study. So there's really a lot of great information already about White Sands and its former inhabitants. And the White Sands resource personnel there, led by David Bustos, who we refer to as the Zen master of the tracks, he's amazing and his staff are amazing, and they've been documenting contemporaneous Pleistocene megafaunal trackways and footprints, and they have a really good idea of the types of animals that were hanging out with the humans. So here's a few of them. From left to right, we have dire wolves. We have saber-toothed cat, so this is Canis dirus, Smilodon fatalis. We have the giant ground sloth, lots of those. Camels, we have mammoths. There are mammoths at White Sands. You would not believe how many mammoth footprints there are. You can actually see mammoth footprints on Google Earth if you know where to look on that alkali flat. And then, of course, the human footprints that are the subject of our little story today. And in the recent field seasons, we've also added short-faced bear and horse to this growing list of taxa that are known from White Sands. So we cannot overemphasize how many human footprints and megafaunal tracks and trackways are present and currently eroding at the surface of White Sands. There's literally thousands of tracks that cover the landscape as far as the eye can see. They're everywhere on the east and west edges of this basin. They can be followed for really long distances. And they are also in the subsurface. Here is a ground penetrating radar image from the alkali flat. The quick estimate here is that there's probably about 10% mammoth, 20% giant ground sloth, and about 70% human or other smaller animals in this ground penetrating radar image. And these prints have yet to be exposed. So these are in the subsurface. It's really remarkable. So the paleoichnology team, paleoichnology are these people that study tracks and trackways, is led by Matthew Bennett and his team at Bournemouth University in the UK. And he and his team have gleaned an enormous amount of data, specifically behavioral data, from these discoveries. One groundbreaking study revealed an incredibly rare example of humans interacting with a giant ground sloth. The tracks are made contemporaneously. They are on the same surface. People are walking alongside the sloth, then up to the sloth. The sloth rears up on its hind legs, I guess clearly annoyed at the people. And an analysis of this sort of track panel, as they call it, indicates that prey selection is happening here and suggests that humans were either harassing, stalking, and or potentially hunting this now extinct giant ground sloth. There's another incredible study at White Sands that documented the longest double fossil trackway in the world. It's 1.5 kilometers long. It's a set of trackways of a small adult human walking one way and then walking back, walking seemingly alone in one direction, as we see originally, with an asymmetrical gait. Well, it turns out that it's been interpreted as that this is a mother holding a child in this outbound journey. So here's the two trackway panels here. This is the actual trackway panel, and this is a graphic of the panel. It's been interpreted as a mother holding a child in this outbound journey. So this is the outbound journey. And on her way back, we see that she sets down a child. And these are teeny tiny feet here. It's almost hard to see, but they're very tiny little feet. She sets down a child. The child doesn't want to be set down, clearly, because she picks it back up and goes along her way. And this entire sequence is 1.5 kilometers long. Between her to and from journey, there's a kind of a lot going on. It gets a little bit crowded because on the left panel here, we see tracks that are transecting the human and vice versa. In this left panel, this is a giant ground sloth that comes along. It hangs out for a while, rears up on its hind legs again, I guess annoyed again at the person. And it does this weird little loop and then takes off in the opposite direction, which is kind of amazing. And the right-hand panel has a mammoth coming along. And you see in the next slide that the woman actually steps on the mammoth. So these kinds of behavioral glimpses are really remarkable. And we see this a lot. We see this human stepping on the animal tracks stepping on the human tracks. And at our locality that we're talking about tonight, locality 2, there's that going on as well. And so here's David Bustos, again, in his normal position, cleaning off tracks. And he's cleaning off these tracks here. In the foreground, there's actually a dire wolf, a big doggy paw print right here. And on closer inspection, the tracks that David was cleaning off are human. So there was a human walking in the view toward us, but the dire wolf came along right after and walked the opposite direction. We don't know how that turned out for the people, but this is what this track analysis indicates. So you see, a lot of work has been done already on the megafauna and the people that were hanging out together. And I'd just like to point out that the discovery of these contemporaneous Pleistocene megafaunal tracks and the footprints of people here at White Sands is unbelievably unique. We're getting remarkable glimpses into behavioral interactions between the two. These new studies are revealing literally snapshots in time into the lifestyles of living, breathing animals and humans that could never be achieved by studying fossil bone or finding artifacts alone. It is the reason that White Sands and its plethora of prints, I love saying that, is singularly unique worldwide for this very fact. And it's one of the reasons it is on the list of potential World Heritage Sites. So as a reminder, the generally accepted timing of when the megafauna went extinct is at the end of the Pleistocene, which is about 12,000 years ago. So up to this point, prior to our involvement in this study, the best published guess as to the coexistence of the humans and the megafauna would have been around that time or older, but that was anyone's guess. So the burning question was, and why the Park Service invited us to do this work, is how old are these prints? And when did the track makers live? So that's pretty much where Jeff and I literally came in. At the USGS, we work in the climate R&D program, and our research involves describing and interpreting pretty much exclusively Ice Age sedimentary sequences, and our focus is on springs and desert wetland ecosystems all over the American Southwest. And we work in a lot of national park units. This image you're looking at here is Tule Springs Fossil Beds National Monument, but we also work in Death Valley, National Park. We work in the Channel Islands, in the Mojave Preserve, in Joshua Tree, and we work in all these places to understand how and when the ecosystems we're studying responded to climate change. That's our hook. We do detailed stratigraphic descriptions, and we create high resolution chronologies, mostly using radiocarbon dating, and we extend these chronologies or augment them with another type of dating called luminescence dating. And we've been able to bracket in time very specific climate events in these sequences, and we discovered that the water-dependent ecosystems that we study respond almost instantaneously to changes in climate. So that's the work that Jeff and I do. And as a cool added bonus, Pleistocene vertebrate fossils are spilling out of the ground in the sedimentary sequences that we study all over the place in these parks and all over. And because of this specific focus that we have on creating frameworks to then study climate, there's been this additive result of providing the National Park Service with the solid stratigraphic and temporal and locational data that helps them manage and protect and interpret their resources. So because of this relationship we have, this is the reason that Jeff and I were asked by the National Park Service for, to assist them. And their specific ask was to evaluate the work that had been done previously in the park and to come up with a methodology to accurately assess the age of the human tracks, as well as to provide this stratigraphic and paleoenvironmental and paleoclimatic context of the tracks. So obviously we said yes, because that sounded really cool. And so we did that with a large team of people. This is the core group that you're looking at here. In the upper left is Vince Santucci. He's the senior paleontologist in the Washington office of the National Park Service. Dan Odess is a retired chief archaeologist in the National Park Service here in the upper middle. In the right-hand corner, in the upper right-hand corner, is Tommy Urban, who's a geophysical archaeologist, and he does this amazing vanguard ground-penetrating radar work in the park. Matthew Bennett is here, Jeff Pagati, Kathleen Springer, and then here's David Bustos in his regular position. So that's kind of the core team that we're working with. So to meet this challenge, Jeff and I brought to the table kind of an overarching approach that really involved a series of questions and tests. And we came at this as the research geologists that we are, not as archaeologists, not as the vertebrate paleontologists or the paleoichnologists, because there was already those people populating this team. We came in as geologists, and we literally had no skin in the game in terms of any kind of prevailing thought as to the arrival of humans in North America. It wasn't even in our brains at all. We approached this study at White Sands with exactly the same methods that we employ at all of our sites throughout the Southwest. So the first question is, are they human? And that sounds like a no-brainer at this point, but it was absolutely critical to ask and answer, because early reports were that these tracks maybe were giant ground sloth, question mark. But the trackway experts can answer that question with their analytical methods, but I want to show you some images to ponder here so that we can all look at these together and at least agree qualitatively that they're humans. So these are bipedal, barefoot animals, let's say. They have a heel and 5 toes, but sometimes it looks like they have 6 toes or 4 toes or no toes. And sometimes they're slipping and sliding and they're just like a big slurp across the mud. It's all a function of the substrate that they're walking on and the moisture content. So I'm just going to scroll through some of these, and I hope that we all can agree, at least again qualitatively, that these are human footprints. But to answer the question quantitatively, Matthew Bennett and his team, they measured the 61 footprints that are at our site, and they compared that data set. They measured the foot in with all kinds of metrics. And they compared that data set to a data set from Africa of habitually unshod people in Africa, and then also compared that to a data set from the UK of people who routinely wear shoes. And you can see here that all of these fields intersect in this multivariate statistical space and indicate that these are in fact humans. Yay. Okay, so they're humans, but further demographic analysis, this is the really cool part, show that these are mostly teens and children between the ages of 9 and 14, which is really super cool. And one hypothesis for this is that there's a division of labor going on here. Whatever they were doing, it's a division of labor where the adults are involved in skilled tasks, more lifting tasks, whereas teenagers can do fetching and carrying, and of course children are sort of the hangers-on, and collectively they leave a higher number of footprints that are preferentially recorded in the fossil record. So that is what we see there at our locality, and we love this mural that basically shows kids hanging out, just checking out the mammoths. We just love this image. So let's get back to it again. How old are these prints? And when did these humans and track makers live? So that's the question. Like, how do you go about dating footprints exposed at the surface of a vast alkali flat, exposed by deflation? Well, as Jeff and I said, you can't. You just can't. Tracks exposed at the surface would only yield dates in the sediments underneath the tracks. If you were lucky enough to find something to date, it would only give you a maximum age, because as we know, everything above is just air. You need to bracket the tracks in time. You actually have to have the tracks encased in sediment with datable material above and below to bracket the tracks in time, to say anything definitive. So we asked, anywhere are the footprints actually found within layers of sediment? Because if you don't know, we need to dig a trench. You need to dig a trench to expose this sedimentary sequence and cross-section and to find the tracks and track horizons in this third dimension. Or as I like to call it, we need to expose the belly of the beast. So that was the idea. And there was a site at the edge of this alkali flat that everyone had in mind because the sediments there are exposed in very low relief. There is stratigraphy there, but it's very, very, low relief. And Jeff and I did a recon there about 10 months before the main excavation, and we collected samples up this section for radiocarbon dating, and the dates looked very promising, and they were in stratigraphic order. But before this site was given the green light, it took this really amazing ground penetrating radar by Tommy Urban to prove that the tracks were in fact present in the subsurface before we could dig. So here's Tommy with his GPR machine running it across that same surface that I showed in the last image. And his analysis reveals, so the top panel, his analysis reveals that there are humans in the subsurface, this black, little tiny black blobs, horizontal, this diagonal, and it's cross-cut here with some more black blobs. Those are all human footprints, the black blobs, that's fun to say. And the bottom panel are large black blobs, and those are mammoth prints. So we were all very excited because, yes, we now know that there are prints in the subsurface, so the green light was given that we could dig. So the excavation started in January 2020. Here's David again, beginning sort of this evolution of the trench. And I just want to point out that White Sands is very diligent, and David specifically, he's done more than any individual to not only discover and champion these footprints and tracks, but he's also meticulously documented them with a GIS-based approach using photogrammetry, LiDAR, and he has utilized the U.S. Geological Survey's drones out there, and they're very interested in quantifying the rates of erosion of these tracks because it's really critical in the resource management of these very fragile resources. The same elements that are exposing these tracks are the same elements that destroy them. So here's Matthew Bennett And he and all of the archaeologists, they spend almost all of their time excavating at the surfaces. They are working on these flat surfaces, and the geologists like Jeff and I, we are in the trench, and we trace the surfaces they excavate into the stratigraphy so that everything can be pinpointed in space and time. The trench is dug entirely by hand using rock saws and pry bars. So here are some of the beginnings of the surfaces. So that's Jeff in the trench, and the archaeologists are on the surface. And here's it farther along. All of these little tags you see here are next to prints. Those are all human footprints, except for that one right there. That's the dire wolf stepping on a human. And then here's a great view of the interior of the trench, and there are footprints at the base of the trench. And you can see the beautiful fine stratigraphy here in this trench as well. And here's David excavating the footprint at the base of the trench. Here's a really wonderful example of what I'm talking about. These are 4 individual track horizons, people on every surface of these 4 track horizons, and you can clearly trace these horizons into the cross-section of the trench. And that allowed us to finally lock them into the stratigraphy. We thoroughly documented this trench. We described the sediments, the stratigraphy with good old-fashioned field notes and drawings, photography, photogrammetry, high-resolution GPS. And what we ended up with was the published composited stratigraphy of the site, and all of the track horizons mapped onto them exactly, showing all of the megafaunal tracks and the demographics of each horizon. Ultimately, we ended up with 8 published track horizons here at what we call, again, locality 2. So now we've documented that the tracks are within the stratigraphic layers. All we needed now was datable material, and we would be golden.
So as Kath said, the footprints are located on discrete surfaces, and so we spend a lot of time looking for material that we can date by radiocarbon. Many of the sedimentary layers that are exposed in the trench, they break along bedding planes, and so some of those bedding planes, when we break them open, reveal dense mats of seeds and stems, and we found a number of thin seed layers in clay-rich sediments that we could use for radiocarbon dating. So finding these seeds in layers is really critical because individual seeds are able to move up and down through unconsolidated sediments over time. So we avoided these since they might not be in place. We also avoided dating something called seed balls, which are basically clumps of plants that have rolled around on the landscape in the Tularosa Basin, since they're obviously not in place either. And a few of the folks that have criticized our work have said that this is actually what we dated, and we didn't. We did not date the seed balls at all. In many cases, the seeds that we actually dated, they were still attached to their delicate stems, and they're found within cohesive layers, so we know that they haven't moved since the plants were alive, which is ideal for dating. So we collected seeds from several of these layers and even from within individual footprints, so there's no question that people were walking around on a mosaic of wet and dry ground and stepping directly on the plants. So we took the samples back to our radiocarbon lab here in Denver, where our colleague Jeff Honke cleaned the seeds both physically and chemically, because obviously we want to date the carbon just from the seeds themselves and not from any of the adhering sediment. The seeds are from an aquatic plant called Rupia serosa, which is a common type of ditch grass that grows in shallow water. And this is on the right is what the plant looks like kind of in life position. This is what we actually dated by radiocarbon. Now, as background, the USGS has had an active radiocarbon lab since the early 1950s, and there have been at least 3 different iterations of the lab, the latest of which is located here in Denver. So let's do a quick review of radiocarbon dating, because the details of this technique actually turn out to be really important in our case at White Sands. The basis for radiocarbon dating begins with the different types or isotopes of carbon: carbon-12, carbon-13, and carbon-14. Carbon-12 is the most common type of carbon. It accounts for nearly 99% of the total, and it's stable, meaning that it doesn't decay away over time. About 1% of all carbon is carbon-13, which is also stable, and then just a tiny fraction of carbon is carbon-14, and this type of carbon is radioactive. Now, carbon-14 is produced in the atmosphere through the interaction of cosmic rays and nitrogen, and it's then introduced to plants through photosynthesis and then into animals that eat the plants. So when plants and animals are alive, they essentially have the same amount of carbon-14 as the atmosphere. But when a plant or animal dies, the carbon-14 begins to decay away at a known rate, which is expressed as a half-life. The half-life of carbon-14 is about 5,730 years, meaning that after 5,730 years, a plant or animal contains exactly half of the carbon-14 that it had when it was alive. After another 5,730 years, it has only a quarter of what it began with, and so on. So in theory, all we need to do is to measure how much carbon-14 is in a sample. Then we can back calculate the amount of time that's elapsed since the plant or animals was alive. And in other words, that's how we calculate the age of a sample. So what can we date with radiocarbon? Well, technically, we can date anything that has carbon in it: wood and bones, shells and tusks, hearts, charcoal, textiles. Even the Shroud of Turin has been dated by radiocarbon. But whether that date means anything or not is something completely different. Now, the samples that we date in our lab, they almost always come encased in sediment. So again, we spend a tremendous amount of time and effort making sure the samples are physically and chemically clean. This is really a critical step in all of radiocarbonating. It's really the first step in the process. The second step is extracting the carbon from the sample itself, cleaning it up, meaning we get rid of the water and other unwanted gases under vacuum, and then we convert the carbon into pure graphite. And we do this in our lab in Denver using what's called an automated carbon extraction and graphitization system, which is really an amazing piece of equipment that essentially allows us to load a sample onto the machine. We press a button, we walk away, and then we wait and we get a text message a couple hours later saying that the sample has been processed. It's an incredibly efficient and consistent machine, and it also records all of the pressures and temperatures of every part of the line throughout the entire process. So we always have a record of how every sample behaved, which is really important. And in the case of the Rupia seeds from White Sands, we then send the graphite off to the National Ocean Sciences AMS facility in Woods Hole, where they measure the carbon isotopes. Now, overall, we were able to date seeds that were positioned above and below track horizons 2, 3, 4, 5, and 6. And when we got the dates back, needless to say, we were stunned because the ages came back between 23 and 21,000 years old. Now, let that sink in a minute. That's 8 or 10,000 years older than Clovis, and something like 5 or maybe 7,000 years older than almost all of the pre-Clovis sites in North America. And not only are these ages old, but we're documenting nearly 2,000 years of human visitation at White Sands in the sequence. For contrast or comparison, most Clovis and pre-Clovis sites were occupied only briefly, maybe for days or weeks, maybe even seasonally for a few years, but we're talking about 2,000 years of human activity a long, long time ago, which is pretty incredible, but it's only incredible if the ages are accurate. So let's talk about that. For plants and animals living on land, all of their carbon comes directly from the atmosphere, which is great for dating, and in most situations, radiocarbon dating is really straightforward and it works really well. But there are some settings in which radiocarbon dating doesn't work as well, and these include things like lakes that are fed by groundwater, or rivers and streams that are fed by groundwater, or springs that are fed by groundwater. You kind of see the pattern here. The reason that groundwater is potentially problematic is that groundwater flows through old rocks. And some of those old rocks have carbon in them, and so some of that old carbon gets into the water and then into the tissues of plants living in the water. So radiocarbon ages of aquatic plants can be anomalously old. Now, this phenomenon, it's called the hard water effect, and it's a really well-known problem in radiocarbon dating, and one that we're keenly aware of throughout our work at White Sands. So how do you know if hard water effects are an issue at your site? Well, ideally, the way to test for them would be to find terrestrial carbon, let's say a piece of wood or charcoal, and also aquatic carbon like Rupia seeds. You find them both in the same stratigraphic level, and then you date them both. And if they give the same ages, there aren't any hard water effects at your site, and you don't have to worry about it. If the aquatic material gives ages that are older than the terrestrial material, however, then hard water effects are present at your site, and you have to figure out how to deal with them. Now, not for a lack of trying, but so far in our trench, we haven't found any terrestrial macrofossils as of yet, so we haven't been able to do this type of comparison. But there are 3 independent lines of evidence that demonstrate that hard water effects are minimal in our samples if they're present at all. Now, the first line of evidence comes from a study that was done by geologist Bruce Allen and his colleagues at a site to the north in the Tularosa Basin. And there, Allen was working on the stratigraphy and chronology of Paleo Lake Otero, and he described a stratigraphic section in detail that had multiple samples of aquatic material that he dated, including both rupia seeds and ostracods. Now, we examined their ages and we were able to develop a really nice age depth model, as you can see here. And importantly, within this sequence, Allen also found a piece of charcoal, a piece of burnt wood. And charcoal does not have any hard water effects at all. So the idea is, if there are really large hard water effects in this basin in our area, as some people have suggested, then the age of the charcoal would be much younger than the aquatic material and would plot far to the left of this kind of gray band here. But if hard water effects are minimal or absent, the charcoal date would fall directly on the line. And fortunately, that's exactly what it does. It fell right on the line, meaning that, at least in a general sense, really large hard water effects don't affect this part of the basin. The second line of evidence is the hydrologic setting itself. Some of the people that have criticized our work have missed the fact that these people and the animals, they weren't walking around in a deep lake or in a groundwater-fed spring system. We can't emphasize this point enough. They were walking around on a mosaic of wet and dry ground in a large area adjacent to the lake. And these people and the megafauna, they were walking around, and sometimes they walked through really shallow water, and we know it was shallow because their footprints are preserved. And shallow water quickly exchanges carbon with the atmosphere. So if there were any hard water effects initially present in these puddles, they wouldn't last very long at all, which again is very good news for dating. The third line of evidence comes from the ages themselves. You know, we've had several archaeologists come up and say, what you guys really have here are probably Clovis people walking around the landscape about 13,000 years ago, and you just have really large hard water effects that make your dates appear 8 or 10,000 years older. Now, the thing about that is that when really large hard water effects are present, they're not constant. They vary over time, sometimes by hundreds, sometimes even by thousands of years. So they don't just add a finite number of years to an age, but they also add variability to the ages. And in our case, many of our samples, they were separated stratigraphically by only a centimeter or two, but our ages are remarkably consistent, with the oldest dates at the bottom, the youngest at the top, and we're able to reproduce ages within individual stratigraphic horizons across the entire trench. This just wouldn't happen if really large hard water effects were at play here. It also wouldn't happen if the seeds were reworked from other deposits and transported all the way across the basin, as some people have suggested. It just didn't happen that way. That is actually realistically impossible. Now, we published these various lines of evidence in 2021, and even though they're powerful, ever since the beginning of our work at White Sands, we knew that we would have to independently evaluate the accuracy of our seed ages using radiocarbon dating of other materials as well as other chronologic techniques. And the reason is that although we have always been confident in the seed ages, we want to develop community confidence in them as well, because we know that the results that we're presenting here today, they mark a pretty radical departure from traditional thought. So to do this, we returned to the site and we collected pollen samples from the exact same stratigraphic horizons as the original seed samples. And we targeted conifer pollen, mainly pine, for dating because conifer trees are terrestrial plants, so the pollen isn't subject to hard water effects. But the conifer pollen, it's also tiny, like 70 microns or so in diameter, so it's really difficult to isolate enough pollen from the host sediment for dating. So this process, this isolating pollen from the sediments at White Sands, it's an incredibly extensive process that took place in 4 different labs across the country, beginning again with the fantastic work of Jeff Honke here at the USGS Radiocarbon Lab in Denver, where he took a kilogram of sediment for each sample and reduced it to only 1 cubic centimeter while retaining the pollen. And then the samples went to the Quaternary Paleoecology Lab at UC Berkeley, where our USGS colleagues Dave Wall and Marie Champagne isolated the pollen further through microsieving, and then through flow cytometry, and then the flow cytometry facility at Indiana University. And there we used a really novel technique for sorting cells developed by the medical industry to separate pollen from other organic material based on the fluorescence properties of pollen, which is really cool. And then finally, we sent the samples off to the AMS facility at Lawrence Livermore National Laboratory, where they measured the carbon isotope ratios. And the results of all of this processing are really startling. On the left is a photograph of a sample in the early stages of processing, and on the right is a photo of that same sample afterwards. And you can see the final product is essentially pure conifer pollen And this is what we dated in our latest study. We also collected samples from within the footprint-bearing sequence for optically stimulated luminescence dating as another independent check of our chronology. And luminescence dating is completely different from radiocarbon in that it is based on the buildup of energy that are stored in quartz grains, whereas radiocarbon dating is based on the decay of carbon isotopes. It's completely different. So the bottom line is that if the seed ages and the pollen ages and the luminescence ages all agree, then it's case closed. You just can't argue that all three of these independent dating techniques gave incorrect ages that just happen to match each other. It just doesn't work that way. Now, the big result here is that all three techniques did, in fact, give ages that are statistically indistinguishable from one another. So the original seed ages were, in fact, correct. So we reported these findings in a paper that was published in Science in October that Kathleen and I are co-lead authors on that we're really happy with. And the paper is entitled Independent Age Estimates Resolve the Controversy of Ancient Human Footprints at White Sand. So the results are really incredible, and the reception from the scientific community has been just fantastic. But even so, everyone always asks, okay, but what are the implications of these results with respect to the peopling of the Americas? Well, if people were here 23,000 years ago during the last glacial maximum, when ice sheets covered much of North America and essentially blocked passage of people migrating from Asia, then the people have had to have been here prior to that, and in sufficient numbers to make a population that sustained itself for that long, for the 2,000 years that we're documenting here. So at some point before 23,000 years ago, there had to be a way for them to get here either by land or by sea. And our USGS colleague Summer Pretorius has a really nice study on Pacific sea ice and ocean constraints on human migration into North America that includes some really interesting windows of time that could accommodate this early movement. But regardless, we want to be clear that our site and the studies that we've been talking about here today, they do not directly address any of the specific migration routes that might have brought people to the Americas. But they do accomplish one really important thing, and that is they establish that people were present in continental North America during the last glacial maximum. But even with all of that, there was still one more question that we had to answer.
And that is, why here? And for Jeff and I, that was a burning question for us, because in our research, we describe and interpret these desert springs and wetland ecosystems all over the American Southwest to understand how rapidly they responded to climate change. And we've discovered they respond almost instantly to abrupt warming events specifically on a regional scale. So naturally we ask, could rapid climate change be the smoking gun as to why these tracks were both created and preserved? And we kind of always come back to this. There has to be clues in the sediments and the ages themselves. The rocks ultimately reveal that these ancient ecosystems responded to climatic fluctuations. So for instance, in this image you're looking at here, these are deposits that represent an extensive ancient marsh that existed all over the Las Vegas Valley. This is Tule Springs Fossil Beds National Monument. That marsh suddenly dried up along with all of the other marshes in the greater Southwest that we've studied during one such rapid warming event. And these abrupt warming events are called Dansgaard-Oeschger or DO events, and they're known to have occurred during specific periods of time during the late Pleistocene, and a series of these are recorded in the Greenland Ice Core record. These are essentially centuries-long megadroughts, and when they occurred, it wreaked havoc on the hydrologic systems we study. At every one of these events in the southwestern United States, it's a bye-bye water, and these ecosystems dry out and they just collapse. So we went into this study with the same mindset. Could we find a paleoclimate signal here at White Sand? So let's get back into the trench. There's dark gray or black gypsiferous clays that are at the base of this trench here. That's the lake. That's kind of the last vestiges of this lake, this Ice Age lake. And then above you see abruptly, there are light colored sediments that represent alluvial sedimentation. These are gypsum sands, and there's thin clay layers in there that represent momentary wet puddles that Jeff was talking about that have these seed layers in them. And this is the part of the record, this light color, where the tracks are found. people are walking around in this alluvial sediment environment, not in a lake. So they're walking around on a substrate that was a mosaic of wet and dry at a lake margin. So let's get even closer. Here's a close-up view. So there's a transition from a lake to not a lake, and it happens really abruptly. Our earliest dates of the track horizons are near the base of this transition, right about where Jeff's fingers are, and date to about 23,000 years ago. And if we look to the Greenland ice core record over here, we see that DO2 occurred at about 23.3 thousand years ago. And that is the very same event that dried up those marshes in Las Vegas and dried up all of the wetlands that we studied across the West. It's a very significant event. So we hypothesized that that abrupt warming event right there is what drew this lake down for its ultimate sort of demise at this edge of the basin and shrunk it, never to return, and exposed a really wide area along this lake margin where the humans and the megafauna could cruise around repeatedly for at least the 2,000 years so far that we've documented. So that was a really, really cool climate signal that we were able to discern. It is, in fact, the smoking gun. There's lots of Pleistocene pluvial lake basins all over the West. We would love to find the same signal in all these lake basins as well. But what else can we learn about the paleo environment during this specific period of time? So we looked to the pollen. We collected the entire sequence for pollen, and our USGS colleague Dave Wall looked at all these samples, and he determined that the White Sands world was a very different place back then. And you can see here, there's arboreal flora, these trees, the spruce, the pine, the fir. Those kinds of trees only exist at much higher elevations in the surrounding mountains in southern New Mexico today. And the non-arboreal shrubs, like the sagebrush, they were probably prolific. There was probably a sagebrush steppe on the sort of the alluvial slopes of these mountains 20,000+ years ago. So this is definitely a last glacial maximum flora, as we call it. And to test that, we collected surface sediments at a small active playa within the national park, and the pollen there consists entirely of the Chihuahuan desert flora that exists today in southern New Mexico. All of this information that you've just heard about taken together in toto is really important to the National Park Service. It's information that allows them to not only manage and protect their resources, which are very fragile, but it also helps them create interpretive pieces and educational products. So here's another gorgeous mural showing humans and animals coexisting at the edge of a lake during the last glacial maximum. And art is a really great medium to effectively communicate to the public all kinds of things, but in this case, it's communicating that the paleo environment was so much different than today, and that climate has always played a critical role in the White Sand story. To go from this type of setting that you're looking at to the largest gypsum sand dune field in the world really illustrates that beautifully. So we have a lot more that we are doing there. Everybody wants to know what's next. We're continuing to work on the original site. We're looking at lots more proxies, including microfauna that is in these sediments, geochemical signatures. We've also expanded to other sites basin-wide. So there was a blip in there after our original work in January of 2020. We had full intention to get back there in a couple months, but we all know what happened a couple months after January 2020, and we weren't able to return until January of 2022. And we got the band back together, and we started opening up this trench again. We wanted to capture the entire story. We extended the trench upwards and deeper and longer. And again, this was all done by hand. You could see Patrick in the slide before working, and we don't use any kind of excavators or backhoes. You could just see these rock saws here, removing the blocks by hand. Ultimately, locality 2 site trench is now 33 meters long and nearly 3 meters deep. Here's a really cool view of the interior of the trench now. Here's Jeff dusting off the sidewalls, but you can see the real intricacies of the sedimentary sequence here. And look at this. Every time we go out there, some amazing thing is shown to us. Tons of new tracks and trackways. These are baby bear prints here. There's 2 giant ground sloths here. This is a bison print. There's a human walking from left to right here. This isn't cleaned off yet, but when it was cleaned off, we see that Mama Bear was right there too. See, look at that. That's the coolest thing ever. And we've been working on the west side of the basin as well, at a place called Locality 1, and we have a beautiful site there that consists of lake sediments that are overtopped by a wetland sequence, and we have outcrop. So here's the beautiful outcrop. We're working on this big basin-wide integration of this story, the hydrologic history, the paleo environment, how it's all related to the humans and the megafauna. And another really cool climate aspect is that these are individual benches that have human and megafauna footprints on them. And they are very analogous to the benches and caps that we see elsewhere all over the Southwest. Jeff and I working that are the result of this abrupt warming. So we're really excited to bracket those in time. But this is what it looks like on those benches. These people are little people. These are handprints. These are little kids playing in the mud. It's like the most evocative, awe-inspiring thing. It's really amazing. And because Jeff and I can't help ourselves, there's a trench at this locality too, trying to figure out the entire sequence. And there's a lot of work to do, and there's a lot of work still to do. We're really happy to come back in a couple years and give you an update. But for right now, we're happy to take questions. Thank you very much for listening.
Oh, thank you so much, Kathleen and Jeff. That was so amazing. And I did read an article a few months ago, and look, you two are together.
I know, here we are.
How about that?
Christy, would you like me to stop sharing or just leave this image up?
Just leave it up.
Okay.
Yep. We'll just, if we need to refer back, at least we have that ready. If you need to flip back to some slides, but
okay.
Yeah, I just want to say, I read an article a few months back in the Smithsonian Magazine about this and wanted to get you guys on for a lecture for us right away. So
yeah,
thanks. Thank you for doing this. And I found it fascinating, and judging by all the questions we got, everybody else found it fascinating. Yeah.
Good.
So
Awesome.
Just a reminder to all the viewers, use that Q&A icon in the upper right to submit your questions, and I'll just kind of go through a few here to start us off with. So, Anonymous posted, can the human species be identified by footprints?
Well, the paleoichnologists, compared it to data sets of modern Homo sapiens, us today. So that's what they have been determined to be. So they all fit within that.
Got it.
Yeah.
Another one from Anonymous. Can we visit White Sands and see these footprints?
Well, this is the deal. Unfortunately, the areas where we are working is part of the park where there's not public access, because White Sands National Park is surrounded entirely by DoD installations in the White Sands Missile Range, and actually the park itself has a co-use area, as they call it. So it's a former military bombing range, essentially, the Alkali Flat. So the public isn't allowed in this area because of safety concerns. But what the park resource managers are trying to do, they're creating all kinds of amazing interpretive products. If you go to the White Sands website, there's information, and there's also videos you can watch of all of us in the field, which is really kind of fun. But they're creating a brand new museum exhibit with all these things, and that's the closest people can get at this point. They are also trying to they're replicating these footprints so that they can show at least replicas of them. And they're documenting them, like I said, with all kinds of photogrammetric techniques. So I know that they'll create a really cool museum type exhibit at the visitor center. But for now, it's not possible to actually see them in person.
Okay, understood.
Yeah.
Yeah, another one from Anonymous. Please comment on the role of humans on the extinction of different species of megafauna, especially the giant ground sloth.
Well, this is one of the really interesting parts of this study, right? Because for a long time, the idea was people came into North America and the megafauna went extinct. Or
That was
that was one hypothesis, that they went extinct essentially at the same time because of overhunting and what have you. But what we're showing here is that, the megafauna hung around, at least most of the megafauna hung around until around, 12,000 years ago. But people were here for at least 10,000 years coexisting. And that's a really different way to think about this kind of situation. So, yeah, I mean, the more we know about this time period, and obviously this is only one study.
Mm-hmm.
This is a very first study of its kind in North America. And it's going to be really interesting to see and how this plays out when more of these same kinds of sites are looked at, what the populations might have been, what the distribution might have been, the whole bit. We just have no idea about that just yet, but it's really fascinating.
Right. Here's a question from Wendy. How can you tell the relative timing of the human and animal tracks? Couldn't they be hours or days apart before the mud hardened? Not suggesting a direct encounter, except where there was evidence of hunting.
Yeah, no, that's exactly right. So if somebody walked, on top of a footprint that was a minute old, an hour old, or a day old, it probably wouldn't look any different, right? They're contemporaneous on the scales that we are studying, right? However, having said that, the ichnologists are absolutely just fantastic at what they do.
Yeah.
Matthew Bennett and David Bustos, they are incredible, and they can see kind of these dances in the mud, these dances in the sand, like what Kath was saying about with the giant ground sloth, and you can see behavioral evidence of things that change when humans get into the picture, right? So a ground sloth is coming by, and whether he saw the person or smelled the person or whatever, there was something
reaction.
There was a big reaction from there, right? So the ground sloth jumps up and circles around and takes off. That wouldn't happen if it was, if it happens because they're
because they are contemporaneous.
Exactly.
Yeah, fascinating. When you got to the part about the giant ground sloth, I had to Google it.
Yeah.
Pull one up to take a look. Oh. Another from Wendy, a comment. She says, please encourage people to visit White Sands National Park, especially during a full moon. So
yeah, it's pretty an amazingly beautiful place.
Crazy.
Yeah.
Here's one from Jeff Knott. He says, most of the footprints are teens. Did you find footprints most of the footprints are teens. Did you find footprints of adults, larger, as well, that confirmed the teen interpretation?
Yeah, there were adults as well, but the preponderance of them suggested that the major grouping, the highest peak, major grouping was children and teens between 9 and 14. Yep. But there were adults.
Absolutely.
It was kind of like a little bit of a bimodal distribution.
Exactly.
Or whatever. Yeah.
Yeah, you can see a big difference between them.
Yeah.
Great. Here's one from Simone. Cool. Please comment on whose ancestral lands these are on and how you all worked with the indigenous tribes here during this excavation.
The National Park Service consulted with 32 tribes and pueblos that claim what is now White Sands National Park as their ancestral lands, and I unfortunately cannot name them all, but they do interact, and we have quarterly calls with the tribes. They are all invited. And they are invited every time we're in the field. There are indigenous folks with us. There is a couple indigenous archaeologists that are part of the team. And there's one woman who we just love, Kim Charlie, and her sister Bonnie, and they are from the Acama Pueblo, and they come out pretty much every time, and they help excavate and do all kinds of stuff. So there is that interaction, but the Park Service definitely reaches out and they're invited, to all the things that we do. And it's actually really super cool. So.
Here's one from Eric Goodwill. He says, you mentioned that there has been some criticism of your work. Can you summarize some of these? And I think he means, do you have work planned to refute these? I think that's
yeah, that was exactly the whole point of the second study. So the first study came out, and we had the dating of the aquatic seeds. We had all of the independent lines of evidence, and we knew even early on we knew we were going to have to go back and date and do different things. When that first paper came out, there were several groups that basically said, maybe, but you need to do more, right? What you need to, and this is the funniest thing.
And we had planned to do more.
Yeah, the funniest thing is that almost all of them ended these kind of comments or whatever they would send with something along the lines of, what you need to do is you need to date pollen and you need to do luminescence dating, because that would really seal the deal. And we're like, exactly, that's exactly right, because that's exactly what we're doing right now. Yeah. So as Cass said, we were the original trench was dug in January of 2020. We had planned to go back in April of 2020 to collect the samples for pollen and luminescence. And then of course COVID hits and all the plans were just blown up. So once we did this second study, and this has been a really cool thing, people that were on the fence or unsure about the results of the initial study that came out, we got so many people that came in and said, you know what, you nailed it, you got it. And this is what we've been waiting for, including some folks that have really been kind of in that
diehards,
first diehards, or this just isn't possible. Looking at the data, when you take emotion out of it, and it's really difficult to do, but when you take emotion out of it and look objectively at the data, and we think it's pretty clear what we have.
Right. Nice. Here's another one. There's about 5 or 6 more here. Cool. Have you found any evidence of small terrestrial wildlife like extinct rodents and lagomorphs?
One of the things about tracks of animals that don't weigh very much, they don't make tracks that they're very ephemeral. They don't make tracks that are preserved. They don't have enough weight to have made tracks that have any kind of permanence in the fossil record. A couple birds have been discovered, and birds are pretty, light. A shorebird, kind of like a water kind of bird. Yeah, I don't think anything that's really little has been discovered at all. They're all the sort of charismatic, big megafauna.
Yep.
Yeah, no, makes sense with the weight. I think you kind of touched on this next one from Anonymous. It says, how is the site being protected from damage by tourists and vandals?
Yeah, well, it can't get in there. And the sites are confidential. They're not published. We don't, in the publications, it doesn't actually say where any of these things really are within the national park, even if you were inclined to hop a fence and walk 5 miles. And
not only that, the trench, there's so much sand that gets blown around there.
Oh yeah, that's important.
The trench that we have dug and that we open up, it gets filled with sand within a week. Within a week, you can't even see that there is a trench in this area. In fact, one of the times we were out there, we opened the trench, we cleaned it all up, and the next day we came in, it was about 3/4 full in one night. Right?
In one night, yeah.
So that's actually a really nice way to preserve the what's exposed in the trench. What's on the surface, basically, as we were talking about this before, the same process that exposes these tracks at the surface for us to study, they also the same process destroys them. So prints that are at the surface that are exposed are gone within 2 or 3 or 4 years. So that's why the National Park Service and David and his crew spend so much time and effort trying to document as many of these footprints as they can at the surface before they go away.
Yep. No, makes sense. Here's another. Are there any archaeological strata? Have you done consultation with the local tribes?
Is there any archaeological strata?
Yes, strata.
Like artifacts?
Well, there is archaeology in this park, but it's younger, and that has been thoroughly documented. It's much younger than what we are talking about, and yes, the tribes and pueblos are consulted with those human cultural artifacts that are found in association with those sites. There's hearths, there is some meager stone, flakes and things like that, but it's younger. It's definitely younger than what we're talking about.
Okay, 3 more here. Richard asks, have you found any animal fossils or human artifacts in the same layers?
What was the first thing? Any what fossils?
Animal fossils or human artifacts?
No, sorry. Yeah. Not yet. I don't know.
Yeah, I mean, in fact, the gypsum, it's such a gypsum-rich environment, and gypsum is really hard on bones. So if there were bones, and they get destroyed really, really quickly. So there aren't any bones to speak of, and we haven't found any artifacts in the trench itself.
Okay. Betsy asks, and this must be in regards to one of the pictures you showed, why doesn't the museum mural show trees?
Because on the flat, the trees were close. I mean, they were like, if you suppress that ecosystem down like 3,000 feet, the trees are going to be close, but there probably never were abundant trees on the actual flat for,
right.
Because most of the flat had a lake on it,
right.
During the LGM, and, it was drawn down, but the way I envision it is that, that sort of high elevation arboreal forest is suppressed, X meters, or, I said feet, but that comes down. And then after that, a little lower in elevation is this sagebrush steppe, as we would call it, on the, kind of on the alluvial slopes. The pollen doesn't have to travel very far when it's been, elevationally suppressed, to appear in this sequence.
Yeah. Exactly. And then the lake basin itself is really wide and it's flat. Really flat. And so small fluctuations in lake levels have big, basically the lake kind of goes back and forth like this, and it's really difficult to grow trees down on the bottom where sometimes it's getting wet, sometimes it's not. So
probably had a lot of this ditch grass we're getting the dates from.
Yep.
Yeah.
All right. Well, we have one more question here from Janice. Have you found human footprints of similar age in the Tule Springs, Nevada area that you mentioned?
No, have not found human footprints at Tule Springs. Sorry. Lots and lots of fossil bone at Tule Springs, however.
Yeah.
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 Okay.
I mean, so just to kind of follow up on that, this study, it's one place, right? The Tularosa Basin is an incredible place. But there are lake basins that are similar to this all over the southwestern U.S. And so, what we expect to see is that when people start looking for these footprints in other basins like the Tularosa Basin, this is the tip of the iceberg, and it's really going to be amazing to see how this unfolds over the next years and decades.
Yeah.
Wow, this is all very interesting. Those are all the questions we had, and I just want to thank you again to both of you.
Thanks
for being our speakers tonight. And I did hear, Kathleen, you mentioned something about future research and coming back to give another talk. So we're going to hold you to that.
Yep, well, we'd be happy to do that when there's more stuff to talk about. Absolutely.
Awesome.
In a heartbeat.
Well, thank you. Yeah. Thank you both. And thank you also to the audience for signing in and joining us tonight. And I do want to mention that if you did want to watch this again or share it with others, Kathleen and Jack's lecture will be available in about a week for on-demand viewing on our public lecture website, which is shown up on the screen here, www.usgs.gov/PLS. On that website, you can find videos of our past lectures spanning the past 30 years of having this public lecture series every month. So be sure to check those out. And if you want to be added to our mailing list, so you'll get notices about these monthly lectures, you can send us an email, which is also on the screen. It's WNCESIC at usgs.gov, and we can add you to the list. And we only send 2 emails a month, so we're not going to overwhelm you. It's just to announce what the lecture is in the beginning of the month and then a reminder at the end of the month. And just one last reminder about our lecture that's coming up on February 29th. USGS research social scientist Sarah McBride will give a talk on communicating USGS science. So until then, thank you again, everyone, for joining us. Thank you again to Jeff and Kathleen, and everybody have a good evening. Good night.
Thank you.
Thank you.
Bye.